This is the chess bot that we created for our group project for AI class. The name of the bot is Wallyfish. Introduction. So for our group project, we decided to make a chess bot. With our background knowledge and the information we learned in this class, we built a Python program that is capable of playing and winning chess games. Although chess bots are a popular project, we wanted to see how competent of a bot we could create. For this project, we followed an article that gave the basic process of constructing a bot that could play chess. Every decision we made to make the bot unique was done with the intention to make our bot as viable as possible. What is our unique contribution to the project? One unique contribution to the project was creating our own convolutional neural network. This was something we spent a large amount of time on, seeing there were so many factors we could tweak for different results. Some factors include how the data is input into the network, activation functions, optimization function, loss function, and the number of layers we used. Other things that we attempted to do to make our project unique were pre-processing the evals and a Stockfish data set attempt.
As a general overview of our methods, we're using a minimax algorithm for the bot to decide its next move, and the evaluation for each position is coming from a trained neural network. The minimax uses alpha beta pruning to hopefully speed it up by pruning off branches that have a lower evaluation. And the neural network is trained on positions evaluated Stockfish, with the goal being to hopefully capture the characteristics of deep evaluations without having to do the large amount of processing required. For our data set, we considered a couple different sources. Our first option was from LeechChess.com's open database, which contains monthly rated games played on their website. But their database is in PGN format. Some moves are evaluated, so using their database would have required more processing to get the data that we're looking for. As an alternative, and the one that we ended up using, was a data set from Kaggle called Chess Evaluations, which has around 16 million positions that are in Fen notation, which is what we were looking for, and they have a Stockfish evaluation, which we can use.
As far as the pre-processing step goes, there were two major components to look at. That is pre-processing the Fen strings and pre-processing the evaluations themselves. So regarding the Fen strings, what we ended up doing was taking in the Fen string and splitting it into 13 different 8x8 bit boards, where each bit board represents a different piece, like a different set of data. So for instance, one's going to be different pieces for white, another's going to be different pieces for black, and then the last one is going to be some, like metadata, so en passant squares and castling rights, etc. As far as the evaluations go, though, this was a little bit of a point of contention that we met in this project. What we ended up having in our best model was capping the evaluations for non-mating positions at 1500. So if you're familiar with chess.com's rating system, this would be plus minus 15. For mating positions, we set those arbitrarily at plus minus 2000, which would be plus minus 20 in a non-sent upon evaluation metric. So the other thing we tried was scaling the data a little bit more, so it wasn't such harsh cutoffs. But as we'll talk about that a little bit later, it didn't go so well.
So in order to load our large data set into the bot for training, we created a custom data sequence class which loads the data from the file in batches and trains on that, so you don't have to load the entire file into memory. And this ended up splitting the data into 16 chunks so that they were manageable to load.
As far as the neural network itself goes, we fit a convolutional neural network was our best model. And some of the parameters which we set for it was having a learning rate of 0.0001. Having a batch size of 64 was key because it did not really like running at higher batch sizes for some reason. That was a bug we never really completely sorted out. We were running this on the full data set, so this is 12 million positions. I gotta change that. It's already chalked. My bad. We use the train and validation set such that we could use early stopping, so the validation loss would be what's monitored as the epochs progress.
So our minimax function, as I introduced before, it finds the best move for a given position based on the trained neural network, and it uses alpha beta pruning. The minimax itself handles checkmate instead of the bot, since it's very easy to check if a position is in checkmate, and it also makes it so the bot will never miss a mate in one, which is very helpful for it to perform well. And our minimax is run at a depth of 3, since deeper depths can't be run in a reasonable amount of time, which was the low depth was a limiting factor to our bot, which we'll talk about in the discussion.
Lichess is an online platform to play chess. It's entirely open source, and some of the developers on Lichess made a Python library that makes it easy for someone to create their own bot. That's what I used to put our neural network onto Lichess so that anyone can play against it. The vectorized code takes in a fen string as an input, and then it's going to output, as mentioned before, those 13 8x8 arrays. The first array is a representation of metadata about the position. So you can see in the example output, in each corner, there's a 1. That means that both sides can castle king or queen side in this position. The turn player will have their king highlighted, so we can see from this position that it's black's turn to go, because in the first array, where the king would be as a 1. And then every other vector is a representation of a different set of a different type of pieces. So I believe the first array is where white's rooks are. The second array is where white's knights are on the board. And then this gets fed into our neural network, and it outputs an evaluation.
The process DF code demonstration, this is how we're actually inputting our Kaggle CSV into some sort of Python code to be able to output it in the aforementioned ways. So the vectorized function is built into this process DF. It just makes it it takes it out of the 13 8x8 array ways and flattens it completely into a 1x832. So as you can see on the bottom of this slide, we have the input on the left and the output on the right. So the evaluations are going to be pre-processed in the ways that we talked about earlier, and the fen strings are going to be pre-processed in the same ways the vectorized did that you saw last slide. As far as results go, this was a difficult thing to try and nail down for our project. Of course, chess is a very complex game. It's difficult to say explicitly what's correct and incorrect. So what we have though is that on the left side of the screen is the output from fitting the neural network. You can see the loss was going down, but it kind of plateaued at the end. What's not shown there is the validation loss, which actually did go down alongside with it, and at the end it was pretty comparable. So that's how we know that we didn't have a lot of overfitting in the model. At least we hope we did not, because overfitting would have been a big problem for this kind of a project. On the right side of the slide, we have this graph, and to understand this graph, it takes a little bit of knowing what's going on. So on the x-axis, we have the stockfish ratings, which were originally given in our Kaggle dataset. So this is going to be ordered where the far left side is going to be very negative evaluation, so the position is very good for black, and the far right side is positive positions for white. And then in the middle is where it's about even. What we can gather from this graph is that the y-axis also is the residuals as well. So y true minus y predicted. But anyway, what we can gather from this graph is that on the edges of our distributions, our model does not do a very good job. So basically, in positions which are heavily winning or losing for white or black, the model has a difficult time at trying to predict them. In an ideal world, the graph that we're looking at right now would be a completely uniform distribution, and that best fit line in black would be completely straight.
We always figured that the best way to test this bot was to actually play against it. And I actually have a couple of positions to show how well the bot did. So this is the first game, played against someone who's a little less experienced in chess. Something interesting I want to know is that when the center, a lot of good players will contest the center, so they'll move their central pawns forward. When that doesn't happen, the bot likes to put its knights in the center, which makes a lot of sense because it gives the knights a lot of squares to attack. The game continues. This is something else it likes doing, is sacrificing pieces. I think it's because we're running at a low depth. I think if we were running at a higher depth, it would see more moves in the head and see that this is actually really bad. As said. See, it's moved the center pawns up. And here, Wally finds a very simple tactic. It attacks the king and the bishop at the same time. And it does actually take the bishop. And here it's going to sacrifice another piece. He keeps attacking. The bishop's protected by the queen, so this is actually a pretty good move. Continues to attack the king. Even though it's sacrificing its pieces, Wally has put the black king in its own territory, so it's a lot of avenues where the black king can be attacked. And then here it castles, and then finally black decides to take this queen. Most players might be tempted to take the queen here, but Wally finds checkmate in one move, probably thanks to the min-max function. For the second game, we're going to start in the middle of the game for this one. Wally is again playing white. He's going to attack the queen, black's queen. Now it finds a check. And instead of, it finds another check, finds another check, advances down, and now the bishop is attacking the queen, but the bishop here is going to block the rook from defending this square here. Wally will see that, and then it finds mate in one. And then this is a game that I played against Wally. I gave myself white. It again likes to sacrifice its pieces, not so wisely. It finds a pretty good check, block. But now here's where I started to become impressed with what Wally was doing. I as white am attacking this bishop here. Wally's going to find a really cool idea called a counterattack, where instead of defending or moving the bishop back, it's going to put its knight here, attacking my own bishop that's undefended. But then I'm going to move my bishop away, and Wally's going to let me capture the bishop, unfortunately. I got really excited when I played the knight d5, and then I lost my enthusiasm when it just let the bishop die. But Wally does pick up the free pieces, and then some moves are played. And now here I actually made a pretty big mistake, and Wally immediately capitalizes on that mistake. It moves its knight, so it's attacking both my queen and my rook. I end up attacking its queen, and I expected it to take the knight back, but it instead actually sees that it's attacking my rook here. And then there's one more tactic it finds in this game, which I thought was really cool. So I attack his rook is under attack. Wally's rook is under attack, and it finds rook takes e2, and even though I can take it back, now this knight, which was protected by the bishop, with that bishop off the board, it's no longer protected. So Wally takes the bishop. And then from here, it was a very slow, grindy game that I was barely able to come out on top against Wally. But I was very happy to find that it was actually finding tactics like that. It was really cool to see. And then towards the end of the project, just for fun, we decided to have different versions of Wally play each other. This is the version. White is the version where we trained on 12 million positions. Black is when we trained it on only 10 million positions. We start with the white version, taking the rook, and then defends the knight. And older versions of Wally probably would have sacked the queen here, but this new and improved version actually defends the square and then attacks. It was really cool to see it learn. Then it also, by taking that rook, it sets up a skewer, but unfortunately this version of Wally didn't see it. All in all, I'm very pleasantly surprised to see that Wally was actually capable of finding and deploying some tactics. It was really cool to see when it started playing those kind of moves.
Now for some discussion and where we would like to develop next if we had more time on this project. So our minimax algorithm was limited to a depth of 3 with an estimate of 30 legal moves per position on average, which is 30 to the third or 27,000 positions that must be evaluated each turn at depth 3. This increases exponentially to 810,000 if we were to increase it to a depth of 4. It is possible we could speed up the time it takes per move by passing in all the moves as a batch at once instead of predicting one at a time. And here are also some things that we could do on Lichess that could make our bot faster. We could program an opening book, which is a set of opening moves for Wally to follow so that it doesn't waste time and power running the opening position through its eval function. And then we can use Ponder, which uses the opponent's time to evaluate the position.
We had a lot of fun building this project. I'm Greg. I was responsible for the vectorize function earlier and the Lichess implementation.
I'm Matt. I was responsible for pre-processing the data and a lot of the neural network optimization and then running it overnight and stuff.
I'm Austin. I was responsible for a lot of the neural network development and testing. I made the data sequence class, and I made it so the models can play against each other.
And lastly, I'm Carson, and I created the first concept of a neural network that could be used with our data set.
All in all, we for only really working on this like closely for a month, the bot that we ended up with is actually pretty surprisingly good. It's able to realize tactics which are not immediately obvious, and certainly against lower level players, it's going to take advantage of those and it's going to beat them. So all in all, we think that this project is a pretty big success. But there is, of course, a lot of room for improvement in the bot.